We now examine example 3, a structure that has three members that are pinned to one another at B. Members ABCD and BEDF have a pin in a frictionless horizontal slot at D. The fact that it's frictionless tells us that the only force that's communicated through that pin will be a vertical force, as there is no resistance in the horizontal direction. We want to determine the forces supported by each member. We've said that the first things we'll do in situations like this is try to identify two force members and also look to see if drawing a free body diagram of the whole assembly is useful to us. In this case, neither of those options provides much help. We can see from the assembly that there are no two force members in the structure. The presence of the 8 Newton force at H renders BG a general member, not a two force member, and there are enough connections on ABCD and BEDF so that there are intermediate locations, and those are also not two force members. We also see that if we try to draw a free body diagram of the whole assembly, we cut through pins at G and A, and this will give us a total of 4 unknown reactions, so that isn't much help either. We're therefore left in a position where the best thing for us to do is to disassemble the structure one member at a time and see what we can glean from that operation. We'll begin by drawing a free body diagram of BH. And we'll call this free body diagram 1. When we remove BG from the rest of the structure, we'll have internal forces that occur at B on BG and equal and opposite internal forces that are present on the remaining of the structure consisting of ABCD and BEDF. Then our next operation will be to remove BEDF from the remainder of the structure. We'll call this free body diagram 2. And when we do that, there will be another set of internal forces at B, which will now be exerted on the remaining member ABCD. Finally, we'll take a look at that remaining member and draw its free body diagram. And we'll call that free body diagram 3. Free body diagram 1 will look like this. We have an 8 Newton force here at H, and now we really don't know the directions of the forces at the pins at B and G, so we just have to guess, and we'll let the algebra tell us after the fact whether we guessed correctly or not. I'm going to represent GX and GY in these directions, and BX and BY in these directions. Again, these are just guesses. We should complete this by adding some dimensions here. This is 24 millimeters, this horizontal distance here, and we have 2 sets of 20 millimeter distances here. Our second free body diagram will look like this. We have a 10 Newton force applied out here. And then we have our frictionless pin connection at D. That will result in a purely vertical communication between members ABCD and BEDF. And I'm going to guess its orientation this way. Now, when we separate BEDF from ABCD, we're going to get another set of internal forces at B. They won't be the same as the uppercase BX and BY we've shown on free body diagram 1. So we have to give them different symbols. So I'm going to give them symbols script BX and script BY, and I'm going to represent them this way. So here is a script BX and a script BY. And we have a 20 millimeter distance here. And then we have 24 and 36 millimeter distances here. Finally, our third free body diagram, which I'll put up here, is of ABCD. And we have lots of equal and opposite forces to place on this free body. Since ABCD interacts with BEDF, and I've represented the force on BEDF as positive D up, I'm going to have an equal and opposite force here down. And at B, I have equal and opposite forces both from the internal forces from GB and from the internal forces from BEDF. So from above, given the directions of uppercase BX and BY shown in free body diagram 1, I'm going to have the opposite forces up here, BX and BY. And then from below, with the connection with BEDF, given what's represented in free body diagram 2, I'm going to have script BY and script BX. Again, equal and opposite to what's shown in free body diagram 2. And then I've got a pin at A. And so I'll have forces AX and AY here. These distances are both 24 millimeters here. And I have a 20 millimeter distance here. So there's a lot going on in those three free body diagrams. Before we continue, we should make a list of our unknowns and see if we can establish a procedure for solving for everything we don't know. If I look at these three free body diagrams, my unknowns are GX, GY, uppercase BX, uppercase BY, lowercase bx, lowercase by, ax, ay, and d. there are 9 unknown forces among these 3 free body diagrams. Given that we can write 3 equilibrium equations for each body, we should be able to solve for all of these unknowns. The question then is where to start. If we have a single rigid body, we know that we can solve for all the unknowns if there are just 3 unknowns on a single rigid body. And if we look at 1, 2, and 3, the one free body diagram that jumps out as one where we can solve for anything right away is free body diagram 2. So we'll apply all the equilibrium equations to free body diagram 2, and we'll be able to solve then for script bx, script by, and d. Having done that, let's go back up to our free body diagrams. Now knowing script bx, script by, and d, we can see that we have something of a problem in that both free body diagrams 1 and 3 have 4 remaining unknowns. However, we might note that if we take moments about A on free body diagram 3, the only unknown that will be present in that equation is uppercase by, because the lines of action of the remaining unknowns, ax, ay, and bx, all go through A. So we should be able to solve for by directly by taking moments about A on free body diagram 3. We can then use that information in free body diagram 1 to solve for its unknowns. So after solving for everything in free body diagram 2, we'll go to free body diagram 3, and we'll take moments about A and set that equal to 0, and that should enable us to get uppercase by. Now we can take that information to free body diagram 1, and now we've got just 3 remaining unknowns, gx, gy, and uppercase bx. So we can then use all of our equilibrium equations to solve for bx, uppercase bx, gx, and gy. That gives us 2 remaining unknowns. We'll then go back to free body diagram 3 and complete the equilibrium. We'll take sum of the forces in x and set that equal to 0, and that will give us ax. And we'll take sum of the forces in y and set that equal to 0, and that will give us ay. So that will be our procedure. So for our free body diagram 2, if we take sum of the forces in x and set that equal to 0, we get right away that script bx is 0. If we take moments about b and set that equal to 0, we have a positive contribution from d through a distance of 24 millimeters and a negative contribution from the 10 Newton force through a moment arm of 60 millimeters. That sum is equal to 0, and we can solve for d and find that that's equal to 25 newtons. If I then write sum of the forces in y equals 0, I have d minus script by minus 10 newtons is 0. And given that d is 25 newtons, I now have that script by is 15 newtons. The fact that these numbers turned out to be positive or 0 tells me that I guessed their directions correctly in my free body diagram. We go now to free body diagram 3 of ABCD, and we'll sum moments about A, set that to 0. We have script by, which we now know, minus uppercase by, which we're seeking, times 24 millimeters moment arm, minus the contribution from D, which we now know is 25 newtons, times 48 millimeters equals 0. So if I take 25 newtons for D and 15 newtons for script by and solve for uppercase by, I end up with a value of minus 35 newtons. So in this case, the value of uppercase by actually goes in the opposite direction to what I initially represented. And that's okay, we'll just continue using that value. Having uppercase by now, we can go back to free body diagram 1 and take moments about G and set that equal to 0. We represented by as going up on BG, so that will have a contribution of by times 24 millimeters. And bx is exerting a negative moment through a distance of 40 millimeters. And the 8 Newton force is likewise exerting a negative moment through a moment arm of 20 millimeters. So using the value of by equals minus 35 newtons and substituting that in, we end up with bx is equal to minus 25 newtons. So it turns out that bx and by are both going in the opposite direction from what I initially represented. Sum of the forces in x equals 0 tells us that gx minus bx minus 8 newtons equals 0. And I can solve then for gx, and that turns out to be minus 17 newtons. And finally, sum of the forces in y equals 0 gives me by minus gy equals 0. So gy is equal to by is equal to minus 35 newtons. So after a good start in free body diagram 2 where all of my numbers were positive, here in free body diagrams 3 and 1 I've gotten all negative numbers. Again, that's okay, it just tells me that the forces actually go in the other direction. So finally, I'm left with going back to the free body diagram for ABCD, and I can now write force equilibrium in x and y and solve for ax and ay. Sum of the forces in x equals 0 gives me ax plus uppercase bx minus script bx is 0. And that gives me that ax is 25 newtons. And sum of the forces in y equals 0 gives me ay plus script by minus uppercase by minus D is 0. And that gives me AY is minus 25 newtons. Now to finish this, we should go back and sketch our free body diagrams in with the numbers filled in and just see what the net forces are on each member. So here is BG, and I found that the forces at B, the uppercase BX and BY, were actually opposite to what I originally represented. So what I really have going on here, using my numerical values, I have a 25 Newton of force here and a 35 Newton force here. I've got my 8 Newton force at H, and GX and GY both turned out to be negative, so they're both also in the opposite direction to what I sketched. So I have a 17 Newton force here and a 35 Newton force here. For BEDF, that's relatively simple. I have a 15 Newton force here, a 25 Newton force here, and a 10 Newton force here. Finally, we get to ABCD. We have at D our opposite 25 Newton force here. And now at B, I want to make the point that ABCD really has no way of knowing or distinguishing between these internal forces we labeled as uppercase BX and BY and those we labeled as script BX and BY. What it sees is the net force. And so here what we can do is combine these things. We had uppercase BY actually went in the other direction. It goes up with a value of 35 newtons. Script BY was 15 newtons up, and that gives us a net force up of 50 newtons here. Script BX was 0, but uppercase BX was 25 newtons in the other direction, so I'll put that here. And then at A, AX was in the correct direction from what I guessed initially, but AY was not. So I have 25 newtons here. And 25 newtons here. And so the forces on the members constituting this assembly look like this.